Hi, so today I have for you guys an indicator random variable question with expectation and the fundamental bridge. So here's the problem. This is pulled from my section 5 notes. And yeah, so let's get started. So the problem is for one of his part-time jobs, Will is tasked with sitting in a room and rolling 100 fair six-sided dice for a day. What is the expected number of distinct faces that appear in a single roll of these 100 dice? Generalize this probability to n fair m-sided dice. And my hint is indicator random variables. So the first hint, aside from the actual hint that this might be an indicator random variables problem, is that you're looking to compute the expected number. And usually when we want expected number, it could potentially be nice to represent this number as a sum of ones. So let's let n be the number of distinct faces that appear in a single roll of these die. So number of distinct faces. And let's try to formulate this as a sum. So first, note that n can go from 1 to ... to 6. We can't have more than 6 distinct faces because there's only 6 sides of a die. We could have like different multiplicities of each face. We could have like 100 6s, or we could have 100 5s, and each one of those would just condense to one distinct face. We only have 5s in this roll or 6 in this roll. So that's a hint that we want to represent n as the sum of 6 indicator random variables. So I1, I2, ... I6. And let's let I sub j be defined as 1 if face j appears in rolls, and 0 else. So for indicator random variable problems, I like to first, as you've seen here, I like to first define the random variable in words. And then I will define the random variable in sum of indicators. And then I do a piecewise definition of the indicator. And yeah, so this just like gives me a sort of framework to do any of these problems. Okay, so I'm looking for the expected value of n. So let's just take the expected value. And note that we're going to be able to use linearity. So we use linearity to split this up into a sum of expectations. I generally like to write just pluses and ... dots, but you can write it also with sigma notation. Some problems, it's a little easier to see what's happening when you write it with sums with ... dots. Sometimes it's easier for sigma notation. So now this is up to computing the probability, or well, I guess it's up to computing the expectation of each indicator random variable. Note that the tool I used here is linearity. And now I want to compute the expectation of each indicator random variable, so I'm going to use the fundamental bridge. So for example, the expectation of I1 is going to be the probability that I1 is equal to 1, and also equal to the probability that this stuff, face j, appears in rolls. I guess to be more technical, I want to probably define an event A, and then that event A is going to be this. And this is the probability of A. You generally want to kind of avoid having just like words in your probabilities because that gets disgusting notationally, especially if you're applying Bayes' rule. So we're looking for the probability that face J appears in the rolls. So that could happen in many ways. We could have like 5 of the die have face J. We could have like 20 of the die have face J. They could come in all in the front. I guess if we're doing it unordered, then it doesn't really matter the location. But there's just, as with most binomial-esque things, there's a lot of ways to get A face J. So the way we want to compute this is going to be 1 minus probability A complement, face J doesn't appear in the roll. And we know how to compute that a lot better. So face J doesn't appear in the roll if all of the rolls are just non-face J's. So each roll is face J with probability 1/6. So each roll is not face J with probability 1/6. So this is going to be equal to 1 minus 5/6 to the 100 because there's 100 rolls. So this is the probability for E sub 1, E of I sub 1. And note that this doesn't really matter what face we're talking about. I guess I called this face J, but I guess I really meant face 1. So now we can apply symmetry. So that's our third classic concept in these questions. So I spelled that wrong, symmetry. I think that's how you spell it. By symmetry, we have that all of the I sub j's are equal to one another. So really our sum, the expected value of n, is going to be equal to 6 times the expectation of like the first one, for instance, just by symmetry. So this is symmetry. And we just computed that. It's going to be this. So we have 6 times 1 minus 5/6 to the 100. So this is our probability, or this is our expected number of distinct faces. And let's just generalize this to the M and N case. So I wanted to generalize to N fair M-sided dice. Yeah, and just like you can match up this logic exactly. So this time we're going to have M indicator variables because they represent each of the faces. So N is going to look something more like I sub 1 plus ... plus I sub M. And the expectation of I sub 1 is going to look like 1 minus, and there's again M sides, so M minus 1 to the M, or over M. And this is the probability of not rolling a certain face, not rolling face 1. And we're rolling n times, so to the n. So this is going to be our expectation. And then this gives a total expectation of En equals M times 1 minus M minus 1 to the M. So just some like fun things I like to do when I get to a general form like this. And also like finding general forms like this is something that you might see in like interviews. For example, if they ask you probability problems, sometimes they ask you for like a small case, and then later they'll ask you to do a bigger case and then eventually the general case. So this is something I see not just in Stat 110, but also I guess in the job search. So something you can do to sanity check yourself is start taking these numbers to infinity. So for example, let's take n to infinity. So as n goes to infinity, we have m minus 1 over m. This is less than 1, so m minus 1 over m to the n is going to go to 0. So as n goes to infinity, we have m times 1 minus 0, which is equal to m. As n goes to infinity, the number of expected number of faces is going to be m. And this makes sense because we would hope that as we roll infinitely many die, we would hopefully get a representative of every face in this roll. Like there's no face that's just going to not want to show up, causing the number of distinct faces to be less than the maximum number of faces we can get. And I guess you could also check out what happens as m goes to infinity. This is going to be a little weirder because if we have fixed n, then like that n could be like kind of really small, forcing the number of distinct sides to be n. But let's just see what happens. If m goes to infinity, we have the coefficient in front going to infinity. We also have like this going to 1. So I would think that this goes to 0. It would be like infinity times like 1 minus 1 equals 0. But I think this is just not really something we can like think about. So let's just disregard this analysis. And this analysis makes a lot more sense anyway, since it makes more sense to be increasing the number of dice we are rolling as opposed to the number of faces on each number of faces on a fixed number of die. Since I think generally that would be bounded by the number of distinct faces you would get is bounded by the number of die you're rolling. So yeah, this is my problem relating all of indicator random variables, linearity, fundamental bridge, and symmetry. Hope this helps, and good luck on the midterm if you're watching this before the midterm. Good luck in life if you're watching it after.